All right.
So I have a question.
Yeah.
So what is exactly the definition of the control volume?
Contravariant.
Control volume.
Control volume. It is nothing but just a volume. You're just tracking that volume as it is going through the fluid. There is nothing specific about it. Okay. It can be any shape.
For
It can be.
example, there's a container containing some water.
Hmm.
We consider an arbitrary region
Hmm.
of that water and we say it is a control volume.
Yeah.
Now, these water molecules always move
Yeah.
in the container. So, will the control volume will it be changing like
No,
at
no.
the
You
instant
so
of
you,
time?
it, you can choose it. I mean, you can make the control volume stationary also, and you can have the control volume moving also. So it doesn't matter. Okay.
Okay. So the control volume is like not related in with the water molecules inside the control volume.
Yeah. That has nothing to do with it. So whoever is Ajay Nani 183, Ajay Nani 183.
Yeah, sir, it's me.
Yeah, please stop recording.
Hi, sir.
I am recording it on my end. So anyway, so to answer, I think Sheikh Muhammad Ishaq had asked, right? So you don't need to constrain it into anything. You can have control volume static, fluid can come in, fluid can go out. Okay, you can have the case where control volume is moving with the fluid. You can have the case where control volume is moving with some other velocity other than the fluid also. All right.
Yes.
So there is nothing hard and fast about what the control volume is. But I mean, it's a good question because when we will start the lecture next week on conservation of mass, especially the integral formulation, right? You will see that depending on the problem at hand, it is beneficial sometimes to use a static control volume, and sometimes it is more convenient to use a moving control volume. But all that depends on your experience. I mean, you can see and sort of choose what kind of system you want. Okay, so let's take some problems. Hmm, let me see. Okay, so question one. Please mute yourself. Come on.
Good afternoon, sir.
Yeah.
Sir, I have a doubt. Can I ask now?
Okay, fine.
Sir, Basically, you explained Rij, you gave an equation Rij equals to minus epsilon Ijk into omega k.
Yes.
So, there you gave the reason I saw the video again, but I could not understand it clearly. What was the purpose of using epsilon Ijk? Can you explain it with a small example?
There is no purpose as such. It is just to relate a second order tensor to a quantity which is only first order. So it's relating a tensor to a vector. Okay. Because the Rij components are more readily physically understood through the vorticity. Alright. Instead of representing it in terms of two indices, you can simply represent it in terms of the third orthogonal index. That is what the advantage is. I mean, for advanced fluid mechanics, it gives us a lot of insight if you use a single index. Okay. Alright, so let's continue, I guess. Okay. So let us consider the first question. Consider a steady 2D flow with components as shown. So uv is equal to sy comma sx. Alright. So the first question is, what are the equations of the streamlines? Second question is, components of the strain tensor. And the third question is, components of rotation tensor. And alternately, what is the vorticity? And lastly, we want to find a coordinate system which diagonalizes the rate of strain tensor. Okay, and we also want to find out the principal strain rate. Just let me give me a visual clue to cut the video from here. Okay, so you might be, I mean, whoever has done the assignment might be aware of this question. So, are you aware of this question? You might have done this in the assignment.
Yes, sir.
Okay.
Yes, sir. First one.
Yes, sir.
So, let me also do it, right? Just for completeness, whoever was confused in all this, just for completeness. Because I have also made some program to visualize all this. So, alright, so let us go to the next page. Come on. So the equation of the streamline. So the streamline is parameterized by the relationship dy by v is equal to dx by u, and this relationship essentially implies that the streamline, whatever the equation of the streamline is, that is whatever dx and dy will be incurred in going from point A to point B, whatever the dx and dy will be related, and that slope will be the same as the local slope of the velocity, meaning the velocity and the line, the slope of the line will be collinear. So this is the mathematical equation which quantifies that particular fact, and so thus we have dy upon v is equal to, so v in this case is s times x, and this will be dx upon u, which is s times y, and this essentially implies y dy is equal to x dx. So s cancels out, and you can integrate this keeping variable limits. So this becomes y square upon 2 is equal to x square upon 2 plus constant, and essentially I can sort of absorb this particular half into the constant, and I can write y square minus x square equal to constant. So now let me head over to MATLAB because I also want to show you how to actually reinforce your learning. All right. So let me quickly change the screen share. I think it is better for me if I can share the screen completely. Mm, yeah. So right now you should be able to see the entire screen. All right. Are you able to see the screen?
Yes, sir.
Yeah.
Yes, sir.
Okay. So let me head over to MATLAB. Let me create a new file. So first task is I'll clear all the variables in CLC. Alright. So now let us define the domain over which we want to make the plot. So I will make x equal to linspace -2 to 2 and I will take say 20 points. Y equal to linspace -2 to 2 and I will take 20 points. Then I will define a mesh grid. So I'll explain you what these terms are, don't worry. And I'll define the u velocity, so which is basically y, and the v velocity, which is essentially x. I've chosen s equal to 1 in this case. And now with this, I can first draw the vector plot. So I will say figure 1, quiver, x, y, u, v. And let me make, okay, let's just do this preliminary plot. Let me save it as, what kind of flow is this? So dimension 2 flow. Okay, so the flow looks something like this. The flow looks something like this. In fact, let me make it prettier. Okay, let me make it slightly more appealing to the eye. So to make that, I'll do d aspect 111 axis tight. So let's see. Yeah, this looks much better. There's no waste of white space. In fact, let me make the whole thing dark. Let me just copy a snippet of my own program. Okay, so let me just quickly put some labels on the axis. I'll explain you the entire thing, don't worry. Alright. Okay, so we now have a pretty looking figure, and anyone who has watched YouTube, especially the channel called as 3 Blue 1 Brown, I don't know if anyone is aware of that. So this is the aesthetics that
Yes, sir.
that person is looking for. So there you go. Now you know how to do that kind of aesthetic plot. So what can you tell from this particular plot? What is the inference of this? If you just look at the arrows, can you tell me what you can understand by just looking at the arrows?
Velocity of a fluid particle.
Hmm? Someone just said a hyperbolic flow, and that is correct. because that equation that we obtained is actually that of a hyperbola. So no surprises over there, right? But so if you like to track this direction, try to draw a tangent in your mind. It will look something like this, right? Something like this, and this particular tangent will go straight to the origin. The one at 45 degree over here and over here, this will exit the origin and go straight. This will come in from the infinity to the origin. This will go away from the origin to infinity. So those are like the directrix. If you remember these terms, the directrix. Anyone remembers?
Asymptote.
Asymptotes. Sorry, not the directrix. And there will be four different set of flows. One is, so each of those asymptotes will sort of isolate a certain flow. So this flow, this flow, this flow, and this flow, those are sort of isolated by those lines. Do you agree with me on this? So in fact, let us draw those lines also. Okay, let us draw the streamlines. Let's not waste any time. Let us draw the streamlines as well. So I will go over here. I will say hold on. I'll remove this draw now because we only have one figure. So hold on. Streamline x comma y comma u comma v. Then you have to give the starting points. So let's say start x, start y. In fact, let's see what this gives us. There's no start x and start y. So let's start x. Rather, let's start y b. Okay. So obviously I've forgotten the syntax. So it's stream. Start x and start y are the same size. Ah, all right. So okay, let me give it a better color. So let me make it yellow and let me increase the line width to 2. Okay, now what seems to be the error? Hmm. I mean, this sort of thing happens, so nothing to be too flustered about. UVW. Where can you change the options? What are the options? Oh, they don't have any options. Anyway, is the line width. Well, I'll fix this eventually. This doesn't look good at all. In fact, I can make this. Sorry for the contrast. Okay, so if you look at this figure now, what I've essentially done is I've taken a bunch of initial points. If you look at this, the streamline function takes the domain, the velocity field, and it takes the starting points into the picture. So this is, I mean, I'm not drawing the analytical streamlines, I'm drawing it numerically. So this is done using numerical integration. Okay, start x and start y, you're giving the starting points. And the starting point, all the y points are distributed from minus 1.5 to 1.5. If you look at this line, so it's starting from here, and in steps of 0.15, it's going towards 1.5, and all the x points are 1.5 times 1. So it is all the starting points are 1.5. Okay, so x equal to 1.5, and the y values are incrementing. So if you start off at a point over here, so basically this point is x equal to 1.5 and y equal to minus 1.5. So you see it goes straight towards the origin, and because of numerical error, it sort of catches this other asymptote, but actually it will not be there. But the other points, you look, it's going like this. At all those points, the velocity is tangential to this curve, similar to this curve, similarly to this curve. Okay, so let me go back and actually not do it using numerics, but let me plot it. Okay, so let me define psi as the function. So basically this function I can write down as phi is equal to y square minus x square, right, where phi is, or y square minus x square plus constant, right? So depending, so I will now draw the, okay, let me do it one step easier. I'll simply draw the function z equal to y square minus x square, and for various z values we will draw the function. All right, I is equal to y square minus x square. So then we will draw contour x comma y comma psi. Let's draw 20 contours. Okay, so the contours are essentially iso x y square minus x square. So what's a contour? If someone says what's a contour, contour is a line which joins equal locations of equal values. Okay, so all the points on a given contour, all of them will have an equal value. In our case, we have tried to draw a contour of phi equal to y square minus x square. So depending on what value the computer chooses for phi, you get a different contour. Is it clear what I'm saying? So that means that it has colored it. So this particular yellow contour has a certain value. This particular greenish looking contour has a certain value. This yellow contour has the same value as this contour. Alright. So now if I want to isolate, if I want to draw a certain value, I can tell the computer that okay, I don't want all 20 contours, I just want the contour for a certain specific value. Alright. So let's go to MATLAB. Instead of saying I want 20 contours, I can put square brackets and I can put in the values. Suppose I want the contours for 0.5, 0.5, 1.0 and 1.5. I only want these particular contour values. So let me run the program. So these are those contour values. So Okay, which value is 0.5? Okay, let's only draw 0.5. If you want to draw only one contour value, you just put the same value twice, because that's like a semantic you have to follow. Okay, but if you have multiple contour values to plot, you just put in all the contour values and you'll get it. So this is that 0.5 contour value. Let me draw 1.5 contour value. So I'll put it 1.5 twice, and I will execute only this part of the code. So the yellow curve is the 1.5 value. Now what about these values? What about these values? So obviously there will be a change in sign. So let me draw minus 1.5 values. So great, this is the minus 1.5 contour. Alright, this is the minus 1.5. Let me draw minus 0.5. So this is that minus 0.5. So with the help of this contour function, you can draw the streamlines. Or you can use, I mean, if you know the analytical function, you can use the contour function and draw the streamline. If you don't have the analytical function, if the velocity field is too complicated, then you can find it using the function as well. But you have to give initial seeding points. You have to give the initial starting point with the help of which you can draw the function. Now you can say that these lines are a bit jagged, and that jaggedness is because of my choice of grid resolution. So I've only taken 20 points. If I take 100 points, it will give us much smoother lines, but at the same time it will give us a very dense array of arrows. It will give us a very dense array of, so there are too many arrows in this, but the lines are now smooth. Are you seeing this? The arrows are still there, but now there are too many arrows. You have to zoom in to see those arrows, and the streamlines and the arrows are parallel. Is it clear, guys?
Yes.
Yes, sir.
Yes.
Okay, so let me get rid of this. Let me reduce this for future purpose. I'll be putting all this in the television recording because it looks pleasing. Alright, so contour. I can hopefully change the color over here. Excellent. These are the contours. Right. So now let's move on to the next question, rather than the next part of the question, which is the component of the strain tensor. Actually, we want to find the components of both the rotation tensor and the strain tensor. So might as well find out the velocity gradient tensor. So the velocity gradient tensor is del xi of uj. So that is del x u, del x v, del y u, del y v. Is it clear how this comes? Because see, this is basically the first component, I equal to 1, j equal to 1. So del x1 u1, I equal to 1, j equal to 2 is this component. So del x1 u2, I equal to 2, j equal to 1 is this. So del x2 u u1, and this is I equal to 2, j equal to 2, and this is tantamount to this. So what are the components of this? So let us recall that the velocity field is given by u equal to sy and v equal to sx. So this becomes del u del x is 0, del v del x is going to be s, del u del y is going to be s, and del v del y is going to be 0. So now that we have the the velocity gradient tensor, we can symmetrize this tensor. I mean, we can decompose it into the symmetric part and antisymmetric part. So what are the components? So this is the Sij and this is the Rij. So what is Sij going to be? Sij is going to be simply half of 0 S 0 plus the transpose of it is going to be the same thing, right? So this is Sij. So this is tensor S. So this becomes 0 S S0. Okay, as simple as that. What about R? R is this minus this, and it will be 0. So what does it mean to have a 0 rotation tensor? It means that there is no angular velocity, right? And we should be able to somehow gauge this from some kind of simulation also. And what does this mean? This means that the velocity field is such that if I have an element like this, the gradient in the u velocity will cause it to become like this, right? What else? If I have an element like this, the gradient in v velocity will cause it to become like this. Is this statement clear? Whatever I just said, statement A and statement B. If it is not clear, you can ask, no problem. Okay, so then we expect the element to deform in this particular manner. Because of the gradients in the velocity, we expect the elements to sort of change direction. But if you see this shift in the element and this shift in the element, will sort of try to balance out. If I draw this final shape over here, the angle between them is still 90 degree. All right. So that is why it seems to have no rotation. Is it clear the physical meaning of this? If you have an element like this in this kind of a flow, okay, it's not exactly an artist, but so because of the gradient in the u velocity in the y direction, this particular straight line segment will become something like this. Because of the gradient in the x direction, this particular line segment will become something like this. So this original 90 degree is still being maintained. So the physical intuition is clear, is it not? So if it's not clear, let us go to MATLAB and let us see how we can clarify our intuition. I've taken the liberty to do this entire program. In fact, I've done it for a circle, but I don't want it for a circle. I want it Yeah, so the velocity profile is over here, u equal to y and v equal to x. Alright, is it clear? U equal to y and v equal to x. This is the important part. Everything else is to just make everything look pretty, nothing else. So let's do it. So let's run this file. See how this looks. Okay, maybe the time step is too small. Yeah, time step is too small.
Sir, the elevation with the x-axis must be opposite to the elevation in the y
Yeah,
direction.
yeah. One moment. So you are sitting near a mill. You can hear all sorts of mill noise. So this square element is deforming like this in the flow. Is it clear? Okay, so the 90-degree thing that I just told was wrong, and the fact of the matter is something else, like someone just pointed out. It will be opposite, and those elements will come together, but the direction of coming together is different. So what's happening is becoming something like this. So whatever rate this has rotated is the same rate this has rotated. Okay, and hence there is no net velocity, and hence this is zero. So whatever that earlier reason that I said was incorrect, that was incorrect. So the real reason is whatever this rotation you get of this segment, this counter rotation by of the other segment. So the net velocity. So this is cancelling out this velocity, because velocity we have a sign convention of anti-clockwise being positive. But the strain exists, the rate of change of this angle, it exists, and that is manifested through this particular term. Is it okay? Everyone, I hope you understood that the
Yes, sir.
earlier explanation was incorrect. It was wrong. Okay, this entire thing was wrong. I mean, this was correct in a sense, but this was wrong. Okay? In this particular case, it will actually have a rotationality. Why is that? Because this is rotating by this angle, this is also rotating by this angle, and both the velocities are in the same direction. That's why it will have some angular velocity. This will not have any angular velocity, and hence it has no vorticity. All right?
So,
Yes.
if we consider a circle, then the circle will become an ellipse.
Yes, it will become an ellipse.
So there will be rotation. How can
No,
we get zero?
the ellipse, you have to consider the principal axis of the ellipse. So let me show that simulation. Thankfully, I've done it. So look at the principal axis. It's also rotating. Okay. Is it fine?
Yes, sir.
But then the last part of the question is where the interesting part is. The last part of the question is they're asking us to diagonalize the strain rate tensor and find out the principal values. Okay, so let us go to our thing. So the strain rate tensor S is this 0 S S 0, and for convenience let us say it is 0 1 1 0. So then we want to convert this into a diagonal vector. We want to diagonalize this matrix. So how do you do that? Anyone? How will you do?
Determinant of S means lambda I is equal to 0
Hmm?
and the eigenvalues and eigenvectors.
So basically they are asking us to find the eigenvalues and eigenvectors. Okay. So what are the eigenvalues of this? So the eigenvalues of this we can find out by subtracting minus lambda times the identity matrix. So this becomes what? 1, 1 minus lambda. So this becomes lambda square minus 1 equal to 0, and it gives us two values of lambda, that is plus minus 1. Then to find out the eigenvalue, rather the eigenvector, so a times x equal to lambda times x. So 0, 1, 1, 0 times x1, x2 is equal to lambda. So in this case, let us choose the first value, which is 1 times x. So what do we have? X2 is equal to x1, and the other equation gives x1 is equal to x2. So we can choose x1 as 1, so the other direction becomes 1. So 1, 1 is one eigen direction, or the eigenvector. And if you normalize it, it becomes 1 over square root 2, 1 over square root 2. So basically this direction is 45 degree from the x-axis. And what about the other eigenvector? So it is this times x1, x2 is equal to minus 1 times x1, x2. So this, the first expression gives us x2 equal to minus x1, and the second expression gives us x1 equal to minus x2. So what do we have if we choose x1 equal to 1? So we get x2 equal to minus 1. So the normalized version will be 1 upon square root of 2, 1 upon square root of, so minus 1 upon square root of 2. So that direction is this direction. So this direction has eigen value as minus 1, and this direction has eigen value of 1. Alright. So then what is the meaning of all this? What is the meaning of all this? It means that
That should be minus 45 degree.
which should be minus 45.
1 minus 1 factor.
Yeah, it is minus 45. I have never said it is anything else. It's the same as this, no? Same direction is the same. Try to understand, this minus sign could have ended up over here also. It made no difference. Okay?
Yes.
So this is the direction. I'm not really concerned about the vector per se. But yeah. So it is minus 1, meaning it will be compressive. Anyway. So what does this entire thing mean? It means that we can choose this coordinate system. We can choose this coordinate system. Okay, I can write it as x1 bar, I can write it as x2 bar. So in the coordinate system x1 bar, x2 bar, or x bar, y bar, instead of having a strain rate like this, I will have a strain rate of this. Okay, I can take the rotated coordinate system, I can rotate the coordinate system by 45 degrees, and I will not have these shear strains. Instead, I will have normal strains. So these are like shear strains, and these are like normal strains. Is it clear? So if these are normal strains, our physical intuition says that if something is shear strain, then it leads to the rate of change of angle. Like we saw, if it is xy oriented, then the angle changes. The angle between these two 90 degrees, it changes. But what about if we take something in the rotated coordinate system? This is the rotated coordinate system. We only have normal strain. So we expect something which is, say, like this, element like this, it will sort of have normal strains acting on it. And we know that the eigenvalue gives us the stretching or compression of the element. So here the eigenvalue is positive, meaning along this direction it will stretch. So the element will stretch in this direction and the element will compress in this direction. So it will tend to become something like this. And the angle between the two green lines will not change because there is no shearing. So let us look at it in the simulation. Please mute your mic. So let us see that happening. Okay, look at the lines. They are just compressing, they are not rotating. Is it clear? So is this clear whatever I just told? Should I run the simulation again?
Yes, sir.
So the green line compresses and the white line elongates. Okay?
Sir, I have a question.
Yeah.
Like in the question, it is asked the coordinate rotation that diagonalizes the strain rate tensor.
Yeah.
So the matrix Sij should be a diagonal matrix.
Yes.
Now it is given that u is equal to Sx
Hmm.
and v is Sy,
Hmm.
and I like my coordinate system is now rotated through an angle theta in the anti-clockwise direction,
Hmm.
so that the new coordinates be capital X and capital Y.
Hmm.
Now this small x and small y and capital X and capital Y are related. Like small x is equal to capital X cos theta minus
Yes.
capital Y sin theta.
Yes.
And then I substituted them, like for small x I have written and for small y I have written, and now S11 will be dou u by del u by del capital X.
Well, you're basically writing down the tensor in a rotated coordinate system. So whatever you're saying is not the correct way of doing it. The correct way of rotating a tensor is something else. And I don't know whether I've covered it in the class or not. After rotation of a vector, did I cover rotation of a tensor? Possibly not. So it is C transpose tensor C. So where C is the rotation tensor. And it's very easy to prove also. I'll send you some resources. Okay. So the formal way of doing it is to rotate the, I mean not to rotate the tensor, but to write down the tensor components in the rotated coordinate system. Nothing else. And whatever you are saying, all that will actually pop up in the mathematics. Not a problem. Whatever you just said, because x and capital X are related, x and capital Y are related. Capital X, capital Y is basically related to x and y both. So that mapping finds its way in describing each tensor component, and the way to do it is through the rotation tensor. That is, in this case, it will be cos theta sin theta minus sin theta cos theta. So it's like the Mohr circle. Basically, in your first year, you might have done Mohr circle. So the mathematics of the Mohr circle is rotation. I mean, writing down the components of stress in a rotated coordinate system. Nothing else. So if you recall what Mohr circle does, given a state of shear, you can find out what the effective normal stress will be, right? Or given normal stress, what will be the maximum shear stress? So basically, you are trying to rotate the coordinate system and trying to map out which angle gives me maximum stress or maximum shear stress, maximum normal stress. Okay, isn't it? If you recall what Mohr circle was.
Sir, well done in that. So done in that way only. Since I have found a coordinate system in which the shear is zero and the normal is maximum.
Yeah, so
So I have got the
I
theta
will
as 45 like that.
I will show you the
Since I have used a more circle formula.
no. So the Mohr circle formula. I mean, okay, fine. If you have used it, well and good. I'll show you the formal way of doing it. Okay,
Okay.
there is a formal way of writing down components of a tensor when the coordinate system is rotated. Okay, but anyone who has understood that yes, that Mohr circle business was the same thing, kudos to you. I mean, if you could make that connection, good on you. Okay, so is it clear this animation? I'll run it one last time. All right, I'm plotting here the rate of the length of this axis and this axis. So the A1 axis is this axis, then the A2 axis is this axis. So the length in the A1 axis increases, the length in the A2 axis decreases, and the increase and decrease are both exponential. Okay, I have also plotted the analytical function. There is small error because the time step leads to accumulation of error. If I reduce the time step, the animation time will be much larger, but this error will go away. All right, but the fact is this growth is exponential, this decay is exponential, meaning uh, let's go back over here. So if I call this axis length as a1 and this axis length as a2, dA1 dt is equal to lambda 1 times a1. This is what you get. dA2 dt is lambda 2 times a2, and lambda 1 was what? 1. So this is dA1 by a1 is equal to dt, and it implies a1 equal to a1 0 exponential of t. And what does this imply? dA2 by a2 equal to minus dt. This implies a2 is equal to a2 naught exponential of minus t. Means that the length a2 decreases exponentially in time, while the length a1 increases exponentially in time. Alright, and the rates of increase and decrease are this eigenvalues. So if you have a stronger eigenvalue in the a1 direction, this growth rate will increase. If you have a larger eigenvalue in a2 direction, it will reduce. But in this particular case, what is something else peculiar that you see? So initial the area was a1 0 multiplied by a2 0. The initial area of the square, if you may, that was a1 0 into a2 0. So let me multiply these two. So a1 into a2 at any other time is a1 0 times a2 0 times e raised to t times e raised to minus t, and this becomes a1 0 a2 0. Meaning whatever the initial area was, that area remains preserved. Is it okay? Whatever the initial area was, that area remains preserved. Let me so the area of the red rectangle that remains preserved. Okay, no one is saying anything.
Yes, sir.
Yes.
All right. So we've spent a good deal of time in. I mean, I'll send you the codes. I mean, I don't know if you guys have MATLAB or not. I'll send it to you either way and have a look. But regardless, I mean, whatever you do, I mean, try to. I mean, see, I cannot enforce this, but try to look at a problem deeply. Okay? I cannot enforce it in any way. Just try to look at the problem in a deeper manner. Hopefully, it gives you more insight, and hopefully, in your life, you can use it somewhere. Okay? But anyway, I mean, I'll give you a list of practice problems from various sources. I'll just put some screenshots and you can have a look. You can mail me in case you have a doubt, and I'll try to find questions with solved answers are also available. Acha, before ending, let's just do one more problem, uh, just to drive home another message. Okay. So the problem is as
And
follows.
how did you know that we have to find the eigenvalues and means how did you connect that?
Eigenvalues are always going to give you a diagonalization. By
Okay.
by the very definition of a diagonalization, eigenvalues are going to give you the diagonalization. Okay? There is no other way. Is it clear?
Okay, sir.
It's as simple as that. The logic is as simple as that. So consider a flow field. We call it a vortex. So consider a vortex. So there are two kinds of vortex. One is a free vortex and one is a forced vortex. Okay. So let us consider the first kind of vortex. So for defining, so what are vortices? Vortices are like loopy structures. Okay, they are closed like circulation kind of structure. So if I have this as the coordinate system, a vortex with the streamline in a vortex would look something like this. All right. So the vortex is typically, I mean, in 2D, it's most easily defined in r theta coordinate system. So this is er, this is e theta. The vortex is most easily defined in a cylindrical polar coordinate system. So it is given that this vortex has ur equal to 0 and u theta is equal to omega naught times r. Okay. So the question is, what is the vorticity? So let us, I'll tell you the formula for vorticity. You don't have to remember this. You can find you can find the formula at the end of any book. They give you the, so vorticity in Cartesian is much easier to remember, but moment it becomes plane polar or rather cylindrical polar, it becomes slightly complicated. I mean, it's not that complicated, and possibly many of you might know this also. 1 by r del r of r u theta minus 1 by r del theta of ur. This is the formula for vorticity in the z direction. Z direction points towards us. So let us substitute the values. So what is this going to be? So this is 1 by r del r of r times u theta is what? Omega naught times r, and this term is itself 0. So what is this? 1 by r. So this is r square. So del r of r square is 2r, and this omega naught remains. So r cancels out, and you get twice of omega naught. Okay. So the vorticity in this kind of flow is twice omega naught. And if you recall, uh, the angular velocity of a element, so half d alpha dt minus d beta dt. If you recall this, so if an initial fluid element, the angles change. So let's say this is alpha, let's say this is beta. So d alpha dt is the the rotation rate of this segment, while d beta dt is the rotation rate of this segment. So half of d alpha plus dt is like the average rotation rate, is it not? So the average rotation rate becomes omega, half of the vorticity. And we have actually seen this also. Okay, we've done this in the kinematics part. But what does it mean? This entire thing, what does it mean? It means that the element is simply rotating like a solid body. There is no dependency on x, y, or whatever. It's simply rotating like a solid body. So if you have a cross in the flow, it will remain like a cross in the flow. In this particular case, it will rotate. The angle between the elements will not change. Meaning, if alpha rotates by this angle, beta will also rotate by that angle. It will not cancel out. And if you want to go one step further, you can find out the rate of strain of this kind of flow. Okay, it will be 0. But so what? How do we visualize this? I mean, we go to the same MATLAB script. Okay, but before even doing that, I mean, you can sort of get a get an idea. Okay, if we have this as the vortex, if we take a line segment like this, okay, so omega r, so the rotation rate of this point, okay, and the rotation rate of this point, the rotation rate of this particular point will be larger because it's located at a larger distance. Is it clear? So it sort of spans more and it again remains like this. So it's sort of rotating like a solid body. It's like a straight rod which is just rotating in the flow. Okay, it's like a straight rod which is rotating in the flow. It's not changing, it's not deforming, meaning the radial direction it's not missing. It does not become like this. It does not become like this. It's like this same rod and it's going around in circles. Okay, so let us go to MATLAB. So I've encoded the values. Let me run it. So look at this square. This is that same flow, and see it's maintaining the angles and it's simply rotating like a solid object. It does not have any deformation. Is it clear?
Yes, sir.
So that's the beauty of it. So this kind of vortex is called as, you get confused between what's it called. It's either it's a free vortex or a forced vortex. But anyway, it gives rise to solid body rotation. Okay, I have to look it up. What's it called? So the next kind of vortex that we have, I think it's a forced vortex, and the next vortex is a free vortex. So let us, before going there, let us find the circulation of this. So circulation, if we have a closed contour, right? The circulation capital gamma is equal to the integral of u dot ds. So what is ds? ds will be, so this integral will become, so u theta into r. So this is the u theta common. U theta is always along ds. All right. So what is ds going to be? It will be 2 pi r d, not 2 pi r. It will be r d theta. Okay. ds is equal to, rather this ds is equal to r d theta. So it's simply this. So it becomes u theta r square into 2 pi. So basically 2 pi r square. What have I written? U theta. This will be simply u theta, and u theta is equal to omega naught into r. All right. So this is the expression. So it is essentially 2 pi r multiplied by the u theta. So the circulation in this particular kind of flow is equal to the velocity multiplied by the circumference of the circuit, the conduit or the periphery. As simple as that. And you can easily show, I mean, there's nothing to show as such, but this streamline is going to be a circle, and that's kind of obvious. The other kind of vortex is where UR is 0. See, in vertical flows, you always have those closed circuits. So you cannot have a UR component. Meaning, if you have a UR component, it means definitely that this streamline has to go in a certain direction. It cannot mean that the streamline can loop back. So UR will be 0, but U theta in this case will be B upon R. Okay, it's 1 upon R dependency. So let us quickly find out what the circulation is. Circulation is integral U theta into ds. So it is B upon R into R d theta. Theta going from 0 to 2 pi. And this becomes what? 2 pi B. So the circulation of this kind of flow is equal to 2 pi B, and it is independent of R. So as long as, okay, there's a small caveat in this, and people who remember a bit of complex theory, as long as you encompass the point of singularity, so R equal to 0 is like a point of singularity. So as long, pardon me. So as long as you encompass the origin, that is the point of singularity, as long as you draw a contour which contains the origin, this will be the value of the circulation. Okay, you can have it any way you want. It needs to be a closed circuit, and it should encompass the origin. All right, so it is independent of the shape. Don't think that you have to take it like a circle. Okay, even for the other case, don't think for a second that you have to take a circular conduit. You can take any conduit. Thus, you will still find the same value of the circulation. It will always be 2 pi r square omega naught. So then you might ask, what is the r? So it's actually twice omega times the area of the thing that encompasses it. Okay, I mean, you can easily show it using Stokes theorem, no problem. You can take any contour, you can apply Stokes theorem, and you can prove this. And I leave it as a home task. I mean, it's not something which you are expected to know at a basic fluid mechanics, but people who are mathematically inclined, you can try to show that. Okay, next, what is the vorticity of this flow? So the omega z expression. So what is the expression for omega z? Let us go back. Basically, it's 1 by r del r of r u theta minus 1 upon r del theta of ur, something like this. So ur is 0, so this term vanishes. This term becomes 1 upon r del r of r times u theta. So basically b, and it becomes 0. So omega z becomes 0. So the flow is irrotational. Alright. So the flow is irrotational. Well, it is not really irrotational. It is irrotational everywhere except the origin. And how do you prove that? So the definition of circulation is closed integral u dot ds, and closed integral u dot ds is integral omega dA, omega z dA. So using this expression, you can sort of um, define omega z as the circulation per unit area. So as you shrink your contour more and more towards the origin, So it becomes like the limit area tends to 0 1 upon A times the circulation. And 1 upon A varies as 1 upon pi r square, and the circulation we've just found is 2 pi b. So it's 2b upon r square as limit r tends to 0. Pardon me. So the circulation, mm, yeah, the circulation is going to be 2 pi b. If you don't contain, if the circuit does not contain the origin, the circulation would be 0. Okay. If you do not contain the origin, the circulation would be 0. And it's not that difficult to show also. So let us take, so if this is the origin, let us take, okay, in fact, I will give it as a home task. I'll ask you to show that the circulation for any contour not enclosing the origin will be 0. I'll ask you to do it at home. Okay. So what happens for this kind of a flow? So if you draw the origin, the nature of the flow is 1 upon r. So if you have this particular line segment, this has a higher velocity than this, right? So this will progress, but this will not progress so much. So if it was a forced vortex, this point would have come all the way to here. But because this has a decaying velocity, this has a larger velocity than this, it remains something like this. Okay, and then something like this. So it's sort of going like this in the flow, but it's not rotating per se. Okay, so it's irrotational in the sense that an angular element, so element like this will tend to remain like this, but it will rotate. So let us do that live coding, because I don't have the code right now, and we still have 10 minutes left, and hopefully we can achieve to do that within 10 minutes. Okay, so c equal to blah blah blah, this is okay. I just need to change the velocity. So ur is 0, u theta is going to be 1 upon r, and that's it. I don't have to make any other change. Okay, so the expectation is a fluid element like this will simply go in circles while it will maintain that shape. So if I take a playing card like this playing card will simply go in circles. Like it will be here, 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 and so on. But in the previous flow, what would have happened? It would have gone like this. I mean, I've shown you that, so you know how it goes. Okay, it's not allowing me to rotate, but you get the point. Huh. Okay, anyway, that's bizarre. Anyway, it's not letting me rotate for some reason, but let's run the program and see. Let's run the program and see. Okay, it will deform, but the angle between the two axes will not change. It will deform, of course it will deform, but the angle between the two axes will not change. Let me run it for a slightly larger time. I mean, okay, that statement is also incorrect. The angle between the two axes will change, but the counterclockwise rotation of one axis will be exactly balanced by the clockwise rotation of the other axis, meaning that the net rotation rate is 0. Okay. Let me make it go to 5. And you have to realize that the larger the time is and the smaller number of steps we have, the error accumulated will be large, so it will not really be a correct simulation. So the rotation of the green towards the right and the rotation of the white line towards the bottom, those are balanced, and the net rotation rate will be 0. Okay, that zero vorticity should be clear, that it does not mean that it is fixed. All right, it means that it is the angles are changing, but the average rate will be 0. So if you have, just telling it one last time, if you have this as the thing, then this rotation rate and this rotation rate are sort of cancelling out each other, meaning that there is no net vorticity. Any doubt? It's been a heavy session, I can realize that. Any doubt? Hello, am I audible?
Yes, sir.
Okay,
Yes,
Yes, sir.
okay, okay.
Yes, sir.